Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we discuss gradient descent, which is a popular optimization method in machine learning. And the goal here is to use basic knowledge of calculus to understand what gradient descent is in 3 simple steps. And to do so, we use linear regression as a motivating example. So what is a linear regression? The hypothesis that we use in linear regression is that the output is connected with the input variable through a simple linear equation. So here x is input variable, or also known as independent variable. We have two parameters, theta 0 and theta 1. That these two parameters are unknown, and that's the goal of training a linear regression model to find out these unknown parameters. And this y hat is our output or predicted value. So output or predicted value. And the goal of linear regression is to find these two unknown parameters, theta 0 and theta 1, using a training data set. So we have a training data set, which consists of these observations, x1 and y1. So x1 is the input and y1 is the corresponding output or label. And then we have x2 and y2. And we have xn and yn. So we have a set of n observations or n training data points. So this is the x-axis, this is the y-axis. And our goal is to find the equation of this line that we know that theta 0 is the intercept and theta 1 is the slope of this line by solving an optimization problem. So now the main question here is, how do we find theta 0 and theta 1? One thing I want to mention here is that this is the simplest form of linear regression because we only have one input variable. In general, you might have multiple input variables, which is known as multivariate regression. And in that case, you have terms like theta 2, x2, theta 3, x3, and so on. But that's not something that we are considering here to just simplify this problem. And I will tell you exactly where the difference is later on in these slides. But that's the problem formulation that we have. And because we call this a training data set, we usually should use a curly bracket here. And if we want to also write this training data set in a more compact form, we can write this as xi, yi, I equals 1 to n. So that's a more compact way of writing this training data set. And n here refers to the number of training data points. So now we have to define the cost function. So the cost function is what we want to minimize to find these parameters theta 0 and theta 1. One thing that is very obvious here, in a linear regression problem, we want the predictions to be as close as possible to actual output values. So what this means is that for each data point, we want yi to be as close as possible to predictions that we find using this equation. Just to explain this more, so in this hypothesis that we have here, x is the input and y hat is the output. So now I can plug in xi here and I will find the corresponding yi. And that's exactly what we are doing here, that we are putting theta 0 plus theta 1 xi as prediction. And yi is coming from our training data set. So that's the actual value. So now we can subtract these two terms. And we take it to the power of 2 because we want to make sure that all the error terms are positive. If we don't raise this to the power of 2, then some error values are positive and some are negative, and they can cancel each other. And obviously, we don't want to do that. So that's why we take this to the power of 2. And now we have to add all these error terms. And we have to take the average. So we divide this by the total number of data points. And this is known as MSE, or mean square error, because we are taking the average or mean, and also we have these square errors. And now we have to name this cost function. Here I'm using J, but you can call it anything else you want. And one thing that is extremely important here is that the variables that we have for this cost function are theta 0 and theta 1. And this might be a little bit confusing because you may say that, oh, the variables are xi and yi's. And the answer to that is that when we have our training data set, we have fixed values for each xi and yi pair. So those things are given to us in our training data set. And the parameters that we're trying to find here are actually these parameters that we have in our hypothesis, which are theta 0 and theta 1. So that's like something to keep in mind here. And if you want, you can also simplify this. For example, this is equal to summation of 1 to n of yi minus theta 0 minus theta 1 xi to the power of 2. And the goal here is to find values of theta 0 and theta 1 that lead to the minimum value of this cost function. So we are trying to find the solution of this optimization problem. And this is what you see in almost any machine learning algorithm, that you have a cost function and you're trying to solve the corresponding optimization problem. So in this case, we want to find values of theta 0 and theta 1 that will minimize this cost function. So the problem here, compared to what you have seen in calculus, is that we have two variables. We have theta 0 and theta 1. So let's first talk about the case that you only have one variable, and then I discuss how you can solve this problem. And also here, I talk about the basics of this method called gradient descent, which is the main topic of this video. So let's say I have a function that looks like f of theta equals to theta squared. So that's theta, that's the y-axis, and I have f of theta equals to theta squared. Based on what you learned in calculus, if I ask you where we have the minimum value of this function, the first thing that you can do, if you don't want to visualize this curve here, you would say that I'll find the derivative of f of theta with respect to theta, which we show by f prime of theta. And because this is a polynomial function, the derivative is 2 times theta. And then we set this equal to 0, which means that theta equals to 0 is either a minimum or maximum value here. There are also other cases too, but in general, we can figure out if it's a minimum or maximum. And obviously here we can see that this theta equals to 0 is corresponds to the minimum value of this function, right? For theta equals to 0, we have f of 0 equals to 0, and obviously this function is always non-negative. So that's why it's the minimum value. This is something that we call this the first derivative test in calculus. You can also use the second derivative test when you have a complicated function to make sure that the extreme point that you found, meaning that those points that they lead to the value of derivative to be 0, they are actually minimum or maximum or other possible cases. But this is a simplified case that we have one variable, we find the derivative, set it equal to 0. So gradient descent provides an alternative way to solve this problem without solving this equation here. So how can we do this? So again, I'm gonna plot this function. So let's say you have an initial guess. For some reason, you may think that theta equals to -3 is the minimum value of this function. So that's the point here. And the idea of this gradient descent is that at each point, you draw the tangent line and you look at the slope of this tangent line, which is the derivative. And obviously here, the derivative is negative. And what this means is that if I go towards the negative side, which is the left side, then the value of this function will increase. And if I go towards the opposite direction of derivative, which would be the positive side here, the value of this function will decrease. And because the goal is to find the minimum, so now let's go to the opposite side of the derivative, and we end up somewhere here. So now you can repeat the exact same process, meaning that you can draw the tangent line. So I erase these. So now you draw the tangent line here, and you see that still the derivative is negative. So now if you go to left, you will see that we will increase the value of the function, and that's not what we want to do. But if we go to right, we are going to decrease the value of the function. So that would be our next step. And you can continue this process. So let me erase this so we can see what's happening here. And we can take all these steps. So this is an iterative process. And then hopefully we get very close to this minimum value, which is theta equals to 0. So that's the basic idea behind gradient descent, meaning that we want to go to the opposite direction of the derivative. So if I want to here write the formula, I can write this as theta should be updated by theta minus alpha, the derivative with respect to theta. So in this case, we have an initial value, and then we subtract it by this derivative times alpha, and that's how we update this parameter theta. And alpha here is known as learning rate or learning step. This is important because you want to know how fast you want to go down the hill here, right? So that's why alpha is a very important hyperparameter that we have to find an appropriate value for this hyperparameter. Otherwise, this technique may not work at all. To explain this more, let's look at the effect of the learning rate or learning step. So if we have the same function and learning rate is too small, so if learning rate is too small, and let's say we start from here, we take all these very small steps. So this means that it takes many iterations to get close to this minimum value. So here it takes too long to find the solution. On the other hand, if the learning rate is too high, what will happen is that if we start from here, then we take a huge step, we may end up here, and then from here, we may have another step, and we may also get farther from the minimum value. And that's what we say that we are diverging from the optimal solution. So here we are converging, and here we are diverging. Although my goal here is not to teach you very rigorously mathematical terms, but intuitively, that's the meaning behind convergence and divergence. So divergence means that we are getting farther from the solution. And in general, if you have some complicated functions, you have to be cautious because, for example, let's say I have a function that looks like this. So here, if you are using gradient descent, and if you start from this point, let's say point A, you may end up to this minimum value. But if you start at point B, then you end up to this point, and we know that that's the global minimum, and that's the local minimum. So to summarize this, gradient descent is a very useful technique, but it's not always guaranteed to find the optimal solution. But it has certain advantages, such as it can be extremely fast, and also it has a lot of variance that can help us to solve machine learning problems on data sets containing millions or billions of data points. So it's a very useful technique, but you have to use it with caution. So right now, there's one point that still might be confusing to you. And that point is that why we call this gradient descent if we have to find the derivative. And that's the point about the part that we talk about the fact that here we have two variables. So derivative is defined when we have only one variable. If we have more than one variable, like here we have two variables, then we have something called gradient, which is the generalization of derivative to multivariable functions. And that's why we call this method gradient descent, because in general, we might have more than one variable. So now, this is the second step here, because if you remember, I said that I talk about gradient descent in three simple steps. So the first step is to set up the problem and to find the cost function. The second step is to find the gradient. And I will show you that gradient is actually not that difficult to find for many cost functions that we use in machine learning. So let's look at that cost function that we had in the previous slide that we called it the mean square error. So we have 1 over n summation from 1 to n of yi minus theta 0 minus theta 1 xi raised to the power of 2. So here, we need to find something that is called partial derivative. So we have to find the partial derivative with respect to theta 0. And I have one video about how to find gradient that I will put the description in the link in this video. But the way that it works is that when you're taking the partial derivative with respect to theta 0, you assume that theta 1 is fixed. So think of theta 1 as being equal to any number that you want, 1 or 2 or anything else. And here, obviously, we have to use chain rule to find these partial derivative. So in order to make this simpler, let's call this z. And now we want to find this partial derivative with respect to theta 0. So this would be summation from 1 to n. And the reason that we can take the derivative of the inside the summation is because obviously they're both linear operators. So we are allowed to take the partial derivative of the inside of this summation. And here we have z squared. So the derivative of z squared is 2 times z. And remember that z is equals to yi minus theta 0 minus theta 1 xi. And now we have the partial derivative with respect to theta 0. So that's the chain rule. Another question is, what's the partial derivative of this term with respect to theta 0? As I just mentioned, for a second, think of theta 1 as being equal to 5 or any other number you want. The partial derivative of yi with respect to theta 0 is 0 because it doesn't have any term that involves theta 0. Then when we have negative theta 0 and we want to find the partial derivative with respect to theta 0, that would be negative 1. And then because we assume that theta 1 is fixed, so let's say 5 times xi, doesn't have anything that has theta 0 in it, so the derivative is 0. So all this means that the partial derivative with respect to theta 0 is 2 over n summation 1 to n of yi minus theta 0 theta 1 xi times negative 1. Now you can use the same strategy to find the partial derivative with respect to theta 1. So let me erase that theta 1 because that's just what we assume to find the partial derivative for theta 0. So now we repeat the same process for theta 1. So this gives us the summation from 1 to n. And then we use the chain rule again. And now we have the partial derivative with respect to theta 1 of yi minus theta 0 theta 1 xi. So now we repeat the same process again. What's the partial derivative of yi with respect to theta 1? It is 0, right? Because there's no theta 1 there. Similarly for the second term, right? Because there's no theta 1. So this means that theta 0 is fixed and the partial derivative is 0. And now we have this term here, and theta 1 is the variable because we are taking the partial derivative with respect to theta 1. And this derivative gives us all the constants that is next to this theta 1, which is negative xi. So this means that now the partial derivative with respect to theta 1 is 2 over n summation 1 to n yi minus theta 0 theta 1 xi times negative xi. So now we have the partial derivative with respect to theta 0. That's the equation we have here. And now we have the partial derivative with respect to theta 1. And gradient is, in this case, we show this by this notation, because we only have two variables. We have the partial derivative with respect to the first variable and partial derivative with respect to the second variable. So theta 0 and theta 1. So now if you have more than two variables, the first thing that you need to do is that to find all partial derivatives and put them together in this vector. So the size of this vector is 2 by 1, 2 rows and 1 column, because we have two variables. And I can write it here as 2 over n. And what we can do here, I can also put this negative 1 inside here in these two cases. And this gives us summation from 1 to n of theta 0, theta 1 xi minus yi. So remember, we are multiplying that negative 1 inside that parenthesis. And the second term would be the summation from 1 to n, theta 0, theta 1 xi minus yi. And then we also have that xi here that we have to put here. Just to make sure that we follow this, we have that term here, and we have this term here. So this is the gradient of that cost function. So now we can use this gradient in this form, but when we want to develop machine learning models, we don't really like these summations because then we have to use a for loop. What we want to do is that we want to use some basic linear algebra tools to write this gradient in terms of multiplying matrices and vectors together. And then the advantage of that is that if we have even, let's say, 100 input variables, then we can write everything in a compact form instead of being worried of finding each of these individual terms. So next, I'm going to show you how we can do that. So here, you need a little bit of basic knowledge of linear algebra. What does it mean if we multiply a matrix by a vector or multiply two matrices together? And I will go through all the steps that we have. So I can write this as 2 over n, so that's the constant we have there. And then I form a matrix that has 2 rows and n columns. So this is 2 by n. And then I claim that I can transpose this original matrix that we have and write it in this form, which is n by 2, because we have n rows and 2 columns. And now we can multiply this by a vector that has theta 0 and theta 1. That's 2 by 1. And then we subtract this by a vector that has all the output values or the actual outputs here, which is n by 1. One thing that I always like to do is that to make sure that the dimensions match and we can multiply them together. So we know that if we multiply these two together, we have 2 is equal to 2. The neighboring dimensions match, so we can multiply them. So that's going to be n by 1. And this vector is n by 1. And this term is 2 by n. Again, n is equal to n. So this gives me 2 by 1. And this means that now the gradient is a 2 by 1 vector. So just to make sure that I put this in the right way, I'm gonna extend this because here we have a subtraction, right? So this is n by 1. And now I add this, so it would be easier to see that. So now these two dimensions match, so we get a 2 by 1 result. So now that we know that dimensions match and we can multiply all these terms together, and feel free to pause this and repeat this process on your own. And I think I erased some of the other terms here that I shouldn't have done that. Okay, so now we have everything that we had. So we call this matrix as X. So this is a matrix X that we call it a data matrix. So if you look at it, each row of this matrix has one of the input data points with a minor difference because here we also added this one to each row. So the data matrix, each row corresponds to one observation or training instance augmented by this constant value 1. And the reason that we have to add this is because of the fact that now we have two parameters here, theta 0 and theta 1. To explain this a little bit more, so we have theta 0, theta 1x in that original hypothesis that we have. So we can think of theta 0 as being theta 0 times 1 and theta 1 times x. So that's why we have always this 1 added to each row. So now, this means that I can multiply these two. And what we have here also is a vector y, which is n by 1, and that's the vector of labels or vector of outputs. And that's what you need in any regression problem. We need a data matrix which has all the observations, where each row is one observation and each column is a feature. And now we have this vector of outputs. And this matrix here is X transpose. So what this means is that the gradient of the cost function is 2 times n, X transpose, X theta minus Y. So that's the compact form that I just told you. And that's the key here, because when you look at, for example, linear regression in scikit-learn, you see that it talks about gradient, and that's exactly what the gradient is. And in general, here, for example, this X, the data matrix is n by 2, but in general, this can be n by the number of features. And remember that the constant 1 is always a feature here. So you always have to add that to your original features that you have in your training data set. So here, one thing else that we can do here is to show why these two things are equal. So you may be wondering that, okay, we found the gradient using those partial derivatives, and now you're claiming that we have this formula for gradient, but you may say that I don't see this immediately. So that's what I'm gonna show you in the next slide. That I will start from, let's call this B, and show that B is exactly equal to A. So in order to do so, we have to do this matrix multiplication here to start simplifying this. So the part B here is equals to 2 times n, and then we have 1, 1, x1, x2, xn. And when we do the first matrix multiplication here, we have theta 0 plus theta 1, x1. And then we have theta 0 plus theta 1, x2. Theta 0 plus theta 1, xn. And then we have the vector of outputs. So you can think of the first vector here as vector of predictions. And this one is the vector of outputs. So I just simplified that matrix vector multiplication. Now we can continue this process. And what we do is that I still keep the first matrix here. and do this subtraction here. So we have theta 0 plus theta 1 x1 minus y1. So we have the element-wise subtraction. Theta 1 x2 minus y2. Theta 0, theta 1 x1 minus yn. So remember that this matrix is 2 by n, and this vector is n by 1. So now we have only one more step. And to see how you can do the multiplication, remember, in terms of matrix vector multiplication, you take the first row and you multiply it by the first column, right? That's how we do matrix vector multiplication. And we're going to multiply all of them by 1. So we can write this as the summation from 1 to n of theta 0 plus theta 1 xi minus yi. So that's the general form of each term. And the only difference for the second one, when you multiply this second row by that column, is that now we have summation from 1 to n of theta 0 plus theta 1 xi minus yi times xi, and then summation from 1 to n. And if you look at this simplified form that we have here, is exactly the same as A that we named it here. So this means that B is equal to A. And that's our second step, meaning that we defined the cost function, which, if you recall, was this mean square error, was yi minus theta 0 plus theta 1 xi raised to the power of 2. So that's step 1. Step 2 is to find the gradient, which we figure out that is x transpose x theta minus y, where x is the data matrix. Each row is one data point or one observation augmented by a 1. So we have 1 x2, 1 xn, so which is n by 2. And then we have the vector of outputs, which is n by 1. And then in the next step, when you want to solve the problem using gradient descent, you initialize the value of theta, and then you repeat this process, that you subtract the current value by alpha, which is the learning rate or learning step, times the gradient. And alpha is a hyperparameter that we have to tune to be able to solve this problem and making sure that the solution is converging to the optimal solution. And this is something that even in neural networks and deep learning, we use to solve those kinds of problems. Although in those cases, we use variants of this gradient descent that are known to give you better solutions. But as you will see in this case, in simple cases, the basic gradient descent will give you a reasonable solution. Like all other videos here, we usually have practice not using Python and packages such as NumPy and scikit-learn to show you how what we learn will apply. And we have other videos on this, but you can use Google Colab, which is provided by Google. It's also known as Google Collaboratory. And you can just create this Google Colab, very similar to Google Drive, and start typing these pieces of code that we have here and repeat these experiments. So here we are going to use NumPy which we use for computing with arrays. And what we are doing is that we are creating the independent variable or the input variable, which is x. And we create these by generating 100 random numbers between 0 and 2, because we are multiplying these x values by 2. And then we are going to create the outputs using a linear equation. So we have 3 times x plus 4, but we have to add some noise. Otherwise, we can just pick any 2 points and draw a line that will go through them so that solving the problem becomes trivial. We obviously don't want to have a trivial solution. So that's why we use y equals 3x plus 4 plus noise to generate the training data. This is known as a synthetic example because we are creating the data set ourselves to then apply gradient descent to solve it. And although this might look very trivial or simple, I think simple is a better term here. This might look very simple. Well, we do this because then we can see how it works and gain intuition about gradient descent. So this is a very common practice in machine learning. And now we will visualize all these training data points. We have X and Y. And we use the blue color. We can use X label, Y label. I will definitely in near future post some videos on how to use Matplotlib and NumPy and some of these tools, but these are very basic stuff and most likely you're familiar with them. One thing that here we need to remember to consider is that when we created the input variables, we always have to add those ones that I just mentioned. So if you remember, the data matrix, which is x, should be in this form. So that's x. And now we also have to add this vector of ones. That's what we have here. That's what we have here. And in order to draw the regression line after solving the problem, we need to have 2 points. So we find the initial point 0 and the point that's the maximum x value. And we use that to find predicted values and draw the regression line. So that's why we added these 2 lines. And this is not something that we're going to use in the training. This is just for prediction part or the testing part. We also, because here we want to explore the effect of the hyperparameter alpha, which is the learning rate, we are creating a function because we want to call this multiple times. As we mentioned, for gradient descent, we always need an initial value. So that's what the first argument is. And alpha is the learning rate. So now the first step is that to find the length of this input data, which we call it x underscore data. If you remember, that's what we call this matrix here, x underscore data. And then we are only use 10 iterations of gradient descent, meaning that we are gonna update data 10 times using this for loop. And in each for loop, we find the gradient. That's this equation here. We have 2 over n x transpose times x theta minus y. That's the same equation that we just found. And then we are gonna implement the update rule, which is theta minus alpha times the gradient. And after we perform these 10 iterations, now we can do our predictions, which we are using the testing data. That's the part that we talk about this. And we multiply it by the theta that we found using gradient descent. And then we are gonna plot the regression line. So obviously here we have not given any values for theta and alpha because this is a function that we define. But now probably you are waiting for this plot that we had at the beginning. So here we are using three different values of learning rates, 0.02, 0.1, and 0.5. So as you see, what happens is that when learning rate is too small, that's the case that is too small. And remember that the first iteration is the one that we show using that red color. So as we see, we are getting better and better in terms of the solutions that we are finding. But because the learning rate is too small, obviously 10 iterations is not enough, right? So we need more and more iterations to be able to find a line that will fit this training data. Then we see that alpha equals to 0.1 seems to be an appropriate value. After a few iterations, we find the regression line that fit the data. But that's like the important part when we choose alpha equals to 0.5. So this is a case that is too high. And what happens, as we see, is that the solution is diverging, right? Because instead of finding lines that are getting closer and closer to the training data, we find these lines that don't even like cross the data, and they are not even close to the optimal solution. And therefore, this means that it is extremely important to find optimal hyperparameter values, which is here this learning rate parameter. So to just summarize this, gradient descent is a great optimization method. And the only thing that you need to find is the gradient, as the name suggests. But make sure that you use appropriate values for the hyperparameter alpha. In future videos, I talk more about how we can choose this hyperparameter alpha and more examples, but I hope you found this video useful.